Lesson 4.5. Find all zeros of polynomial functions. But what if they don't tell you any of the factors? Well, then we have to use the rational zero theorem. Then, if we have a polynomial function, the rational zeros, rational means fraction, zeros that can be written as fractions, includes whole numbers, will be in the form of p divided by q, where p is a factor of the constant term, and q is the factor of the leading coefficient. What this does is, if we aren't given any factors, you could choose anything. This narrows down the choices to something manageable. All right, so let's list all the possible rational zeros of this. Well, we have the p's and the q's. The p's are factors of the constant term, so 9. What times what makes 9? Well, 1 and 9, or 3 times 3. We put pluses and minuses because it could be minus 1 times minus 9, or negative 3 times negative 3. Q's are factors of the leading coefficients, so that's 2. So to get 2 is 1 times 2, and again, pluses and minuses. So the possible rational zeros are p's divided by q's, so I could have 1 over 1, or 1 over 2. Could have 3 over 1, or 3 over 2. Could have 9 over 1, or 9 over 2. There you are. Those are possibilities. Those are not all zeros, but they are possibilities. Having 12 choices, 6 of them pluses and minuses, is far smaller than infinite number of numbers. So let's use the rational zero theorem and synthetic division to find the zeros of a polynomial. So use the rational zero theorem to list all the rational zeros. Use synthetic division to test a possible zero. If the remainder is 0, it is a 0. You can use a graph on your calculator to find the x-intercepts to help choose what you're going to try. You repeat using the depressed polynomial for the next time around, and then that depressed polynomial for the next time around, until the depressed polynomial is quadratic. And then you can find the zeros of the quadratic by factoring or using the quadratic formula. All right, find all the zeros of this function. Now I'm not given any factors, so we're going to take and do p's and q's. So p's are factors of the 20, which would be 1 times 20, 2 times 10, 4 times 5. Q's are factors of the leading coefficient, which in this case is 1. So the p's over q's happen to be the same as the p's. By the way, if you're writing out this list and you end up with the same p divided by q twice, so maybe you had 3 over 1 and 6 over 2, which both give you 3, just write it once. All right, now we're going to do synthetic division. Now, which of these 12 choices do you want to use? Well, usually they're going to be at the smaller end of the spectrum, but to help, we could use a graphing calculator. So go home, pick grapher. Let's put in a new expression. So it's x cubed minus 4x squared minus 2x plus 20. All right, looking at my graph, it looks like I have an x-intercept at the negative 2. So we'll use negative 2. All right, the coefficients are 1, -4, -2, and 20. That was from up here. Bring down and multiply, add and multiply, add and multiply and add. And look at that, you got a 0. It was x cubed. We divided by x. Now it's x squared. It's the depressed polynomial is quadratic, so we can probably just factor that or use the quadratic formula. Let's try factoring. Times x to get 10. It's maybe 2 or -2 and -5, which adds to make -7. But I have 6 in the middle. Well, we could try 1 and 10. It gives me -11. Not factorable. All right, so if it's not factorable, let's use the quadratic formula. All right, so a is 1, b is -6, c is 10, so negative and -6. -6 squared minus 4 times 1 times 10. 2 times 1. That'll be 6. -6 squared is 36, and 4 times 10 is 40. 36 minus 40 is -4. That's why we couldn't factor it. It's imaginary. Square root of -4. Square root of 4 is 2, and the negative makes I. Split that into 2 separate fractions. So just 3 plus and minus 1i. So what are the zeros? Well, it's the -2 that we started with, 3 plus I, and 3 minus I. Yes, you need to have the imaginary zeros for the answers also. If you just looked at your graph and you just found the x-intercepts, you would have only gotten the -2. That's why you have to do the synthetic division to get the imaginary zeros. So how many zeros, how many solutions should you be looking for? Fundamental theorem of algebra tells us. It says if we have a polynomial function, then there is at least one zero. Woohoo! There's one answer, at least. More specifically, it has the same number of zeros as its degrees. So if the degree is 3, there are 3 zeros. If the degree is 5, there are 5 zeros. When we were doing quadratics, there was always 2. We might have gotten a double zero, but there was always 2 for quadratics. Cubics will always have 3 zeros, and so on. They just might be imaginary. Let's try an example. How many solutions does x to the 4th minus 5x cubed plus x minus 5 equals 0 have? And then find all the solutions. Well, we notice it's x to the 4th, so that means there are 4 solutions. It's just whatever the highest exponent, whatever the degree is, that is the number of solutions. Now, to find all the solutions, we can do the p's and q's, or we could try factoring. This one, I see it has a 1 and a -5, and a 1 and a -5, 4 terms. I can probably factor by grouping. Out of the first group, I can factor an x cubed, leaving the x minus 5. Out of the second group, I can't factor out anything, so let's just say we factor out a 1. Then the x minus 5 is the same, so we can factor that out, leaving the x cubed plus 1. Now, if we remember, a cubed plus b cubed, because 1 is the same as 1 cubed, is a plus b, a squared minus ab plus b squared. So that would be x plus 1, x squared, minus 1 times x, plus 1 squared. So then we can take each of those equal to 0 and get x equals 5. Get x equals -1. And then we could try factoring this quadratic. However, when you get the quadratic out of factoring the sum of cubes, it's not going to be factorable, so we're going to have to use the quadratic formula. (b plus or minus the square root of b squared minus 4ac all over 2a So this looks like we have 1 minus 4 is -3. Square root of -3. The square root of 3, and the square of the negative is I. And we would usually split this up into two separate fractions. And so there we have four answers. We have 5, -1, 1/2 plus the square root of 3 over 2i, and 1/2 minus the square root of 3 over 2i. Let's try another one. So we could try factoring this one. Yep, it's not factorable. There are 3 solutions though. So let's try, it doesn't look like a great one for factoring. All right, so let's do p's and q's. P's are, what factors of 10, so 1 times 10, 2 times 5. Q's are factors of leading coefficient. So our possible rational zeros would be 1 over 1, 2 over 1, 5 over 1, 10 over 1. 8 choices. And we're looking for 3 solutions, or 3 zeros. And again, 0 is simply the value of x that makes the function equal 0. All right, so let's pick something. Let's pull out the calculator again. Let's go back and put this one in. So it's x cubed minus 7x squared plus 16x minus 10. And let's look at the graph. We appear to have an x-intercept at 1. So let's try that for our synthetic division. Coefficients, 1 from our function, 1, -7, 16, -10. Bring down, multiply, add, multiply, add, multiply, add. Oh, look at that, we got a 0. It was x cubed, so now we are x squared. That is quadratic. Try factoring it. The 10 could be -5 and -2. Wait, that does not give us the 6. So let's use the formula. All right, b is -6. A is 1, C is 10. So it's 6 plus and minus 36 minus 40. It's -4. So that is 6 plus and minus 2i. Split it up, so it'll be 6 over 2 plus and minus 2 over 2i, or 3 plus and minus I. So our answers are 1, 3 plus I, 3 minus I. 3 solutions, 3 zeros. Notice on our graph where it starts to come back towards the x-axis right here, that is where the two imaginary solutions are. One more theorem, the complex conjugate theorem. If the complex number a plus bi is a 0, then a minus bi is also a 0. So in other words, imaginary zeros come in pairs. Same is true for irrational, which means with square roots. They also come in pairs. If a plus the square root of b is a 0, then so is a minus the square root of b.